Hello all and welcome back. Today's lecture is on related rates, section 5.6 in the textbook, and this will conclude chapter 5. And here's the deal with related rates. A lot of times in real life, things are changing in a way that there's more than one derivative happening. For example, if we think about, say, a cone, and things are changing perhaps in the cone, so maybe the height is changing, maybe the radius is changing, and as a result, the volume is changing because volume depends upon both the radius and the height. And so this is the concept of related rates. As one thing changes, another might change also, but they change a lot of times depending upon each other. And so what we'll talk about here is the strategy for solving these, and then look at a few examples to help understand how to work it. So as before, I've basically grabbed this strategy from the textbook because it's very well done and it helps you approach the problem correctly. So let's go through these steps. Again, as before, you can't begin to solve one of these problems unless you fully understand it, and my suggestion is you don't understand it until you can close the book and explain everything that's going on. You probably also need to talk about what variables are happening, what's constant, what's not, and I like to also here to identify the question. Make sure you know exactly what's being asked. And again, as before, if it's at all possible to draw a picture, do so. It might be a cone, it might be a cylinder, it might be a right triangle, it might be any kind of triangle, but it's very important to be able to visualize as well as algebraize it. It's a nice word, algebraize. Make sure you understand what it is that's changing and what it is that's remaining constant. So at that point, you want to write an equation that takes the variable whose rate of change you're looking for, along with any variables whose rate of change you know. Then what you're going to do is differentiate both sides implicitly, and almost always it's with respect to time. And so you should wind up with an equation that has a rate of change or a derivative that you know and one that you're looking for. Then what you do, and only, let me write it down, only now should you substitute any particular values that you have. The biggest mistake that students make is they plug in specific values before they differentiate, and that's no good. So the point is made here. Do it after the differentiation step. And finally, again, as with any modeling problem or word problem, interpret the solution, which means make sure you answer the question in a sentence and make sure that the answer that you have come up with makes sense. So let's go on and we'll look at an example or two. Alrighty, so here's a typical related rate type problem. Here's what we're told. We're told that water is draining from a conical reservoir, tipped down, at the rate of 2 cubic feet per second. And the question is, how fast is the level of water changing when it's 8 feet high? And we're told that the radius is 6 and the height is 12. So let's make a little sketch here. So my radius is 6 and my height is 12. And you know, at any particular time, the water level might be h and the radius is r. And what we recognize immediately is that r over h, because of similar triangles, is equal to 6 over 12. So similar triangles pop up a lot in related rate problems, and we want to try to grab that information as quickly as we can. So what were we told? Water is draining at the rate of 2 cubic feet per minute. Now, first of all, we know that this is the formula for the volume of a cone. We've got a few too many variables going on here. We got V, we got R, and we got H. Now clearly they are related, and in fact we've already seen over here how R and H are related. Here's the information that we're told. Water is draining at 2 cubic feet per second. What that means is dV dt is 2. But not 2, that would mean that it's increasing. Since it's draining, it's minus 2. And what is the question? Well, we're looking for dH dt at the instant when h is equal to 8. All right, so there is our given information. So now we'll talk about how we go ahead and solve this. Let's pick a new color. Hey, we haven't used that yet. So here's what we know. We know that V is equal to 1/3 pi r squared h, and we know that r over h is 6/12. Essentially, we'd like to get rid of r and just get an expression for V in terms of h, and that's not hard. V is equal to 1/3 pi. Now, what's r? R is equal to 1/2 h, right? So this is 1/2 h squared times h. And if we simplify that, we get that volume, just in terms of h now, is 1/12 pi h cubed. So following the strategy, we now want to differentiate implicitly with respect to t. And so we get dV dt is equal to 1/4 pi h squared times dH dt. And now all we do is plug in what we know. We know dV dt is minus 2, and we know that h is 8. And so if we do all that work and solve it, I trust you can do that, we get that dH dt is equal to minus 1 over 8 pi feet per second. And in passing, let me point out, please, that this condition that h is equal to 8, we didn't use that condition until after we took the derivative. So here's the derivative, and here at this point we'll put in minus 2 here and 8 here, and then solve for dH dt. Okay, so that's our first example. Okay, so let's take a look here. Here we have a triangle, and we have an angle theta, and that is theta, even though I didn't write it very well, is between two fixed lengths. Side A is 2, side B is 5. So they don't change. But what does change is theta. Theta is increasing at the rate of 0.1 radians per second. And the question that we're asked is, how fast is the area changing when theta equals pi over 6? So part of the issue here is we have to get an expression for the area of this triangle. So if we think about side A as the base, I need to know the height of the triangle. And so if I draw down a right triangle like that, perhaps that will help us. So here's what we know. We know that the sine of theta is opposite over hypotenuse. So here's the, call this O for opposite. So sine of theta is opposite over 5. And what that means then is that this opposite side, which is really the altitude of the triangle, is equal to 5 times the sine of theta. So the area of the triangle is 1/2 the base, which is A, times the altitude, which is b times sine of theta. And remember I said that a and b are fixed, so really what we get here is that a is equal to 1/2 times a, which is just 1, times b, which is 5 sine of theta. Okay, so we're asked how fast is the area changing. So dA dt, changing over time, is equal to 5 times cos of theta, and using the chain rule, how important is this, times d theta dt. So now we're asked how fast is area changing when theta is pi over 6. So should have enough room to write this. dA dt when theta is pi over 6 is equal to 5 times the cosine of pi over 6 times 0.1. Now the cos of pi over 6 is the square root of 3 over 2. So what we get is 0.5 times the square root of 3 over 2. And that would be measured in units per second, units squared per second. And so that's another flavor of question that you get with related rates. So I hope they help. You'll have plenty of practice with related rates over the next couple of days. And don't be worried if it takes a little while to get it. This is one of the topics that it always takes 2 or 3 days of practice before calculus students really get the hang of it. So good luck. See you soon.